like to sort of wrap up with a couple of sort of almost forward, current/forward-looking things. So it's a little bit different diagram than you've seen, but same system. But we've included the analysis system on this diagram. And the thing that we wanted to talk about here is that in actuality, the way much analysis of simulation data is performed is in this post-processing mode where the data gets pushed out to storage, and then at some later point is then pulled into some analysis system and ingested in some way, right? Transformed into the representations that the scientists actually want to look at. And there are a lot of advantages to that, particularly if you're using your checkpoint information also for analysis. It's a natural way to analyze the results of simulations. But obviously, we're interacting with the storage system twice, once to write the data and then again to read that data. And so groups are beginning to use alternative approaches to this in order to work around I/O bottlenecks, which in many cases can be thought of as a way to give themselves a greater ability to see the results of their simulations than they would have otherwise, because they're no longer hindered by whatever this sort of aggregate bottleneck to storage is. One approach that we have seen some applications pursue is a co-analysis technique where they take some I/O output that they traditionally would have fired through, say, a parallel net CDF or an HDF, something like that, or maybe use a custom library. But then rather than pointing that data off into a file, instead develop some infrastructure that allows them to write that data directly into application memory on some other nodes. And our colleague Venkat Vishwanath does work in this space under the Glean project. The Adios project, Scott Klasky leads out of Oak Ridge is another example of that. And in some cases is a viable technique. It does have the challenge of a need to co-schedule resources, which isn't always easy, but does make sense. What we also see happening is groups adopting a mechanism of incorporating analysis into the simulation code itself. And so, rather than just dumping out the data that you'd like to analyze, instead you kick off some analysis routines at runtime and perform some amount of analysis while the simulation is still running. It is often requires some modification to the application, which is great if you own the application and not great if you don't, right? Has potential for a lot of efficiency because the data is already in memory, so you're skipping a lot of I/O that you might have otherwise had to incur. And so as an example, you may have seen this example already, actually. This is Tom Paterka's work related to the HAC cosmology simulation and this tessellation operation that they're performing to basically convert from this particle representation that the cosmology simulation uses into an unstructured grid that's really amenable to a certain set of analyses that the scientists want to perform, okay? And I think this example to me is interesting because what is actually happening is that they're using a data model transformation as a way to sort of do a data reduction, and then they're writing this out. So they are actually interacting with the storage system so that they can look at this after the run completes. It's just that they're performing sort of a science-informed data transformation prior to writing their analysis output while they've got all this data in memory, et cetera, that dramatically reduces the amount of data that they have to store. And so in some sense, this is in situ analysis. It is running in the system, but it's also a clever way to allow themselves to do a certain class of post-processing analysis that they might not have been able to perform, certainly couldn't have performed as efficiently otherwise. So the last topic I want to touch on is in-system storage. This is a really hot topic right now in a lot of domains, not just in HPC. When we say in-system storage, that a lot of things fall under that umbrella. The one model that seems to be maybe on the horizon for us is inclusion of non-volatile memory of some type associated with those I/O forwarding nodes that we've talked about 2 or 3 times before. And so rather than simply those nodes serving as a gateway between the compute system and the external storage. They also would have a certain amount of storage of their own. There are a lot of things you can do with that. The thing that has motivated them in HPC, perhaps the strongest, is the notion of using them as what we call a burst buffer. What we mean by that is that what we would like to be able to do is checkpoint. And by checkpoint, really the first thing we need to do is get the data out of main memory so that the computation can continue, right? And then second, we would like that data that is no longer in main memory not to disappear. And so we need to get it out to persistent storage. But you can think of those two things as being separate operations. And so the notion of the burst buffer is to allow for a place where state can be stored temporarily while it's moved off to storage so that you don't have to wait in the normal cost of getting that data out to external storage. Okay, and then if it's big enough, then you can imagine that you sort of fill it up and then it sort of data trickles out while the computation is running, and hopefully it's empty by the time the computation is ready to write another checkpoint, right? And so, then the question is, okay, well, how big are these bursts? How frequently are we going to write them? What difference would this make? And so our group with Rensselaer colleagues have been looking at this problem and using Darshan output as a component of the analysis. And so we said, okay, well, what do bursts look like? Well, back on the Blue Gene P, they were often relatively modest, sometimes in the tens of terabytes, but often in the hundreds of gigabytes. And so that tells us something about the size of these burst buffers we might need at that point in time. And we can sort of think about how we might extrapolate to future systems based on these things and interact with scientists to sort of nail that down. From there, we developed a parallel discrete event simulation that allowed us to sort of feed in workflows and simulate what an I/O forwarding system might look like that does and doesn't have these burst buffers, and how might this trickle, this concept of a burst and then a trickle play out in a plausible system. And so we modeled that Blue Gene P system. And what we were looking at in particular was the perceived performance from the application, right? Because that's really what we're interested in with this little technology is how fast can we return control back to the application and allow them to continue? And secondarily, given our expectation of these burst sizes and frequencies, will we be able to get the burst buffer empty before they come back and provide something else to dump? And it turned out in this particular case, given the workloads that we had to work with and the simulated system that we have, that it was a fairly cost-effective solution to include these. And in fact, we did a separate evaluation where we took the external storage and halved it. We said, okay, well, what if we bought half as much external storage? And it turned out it really didn't make a whole lot of difference, that once we had taken that peak I/O requirement out of the picture, that the sustained bandwidth that we could get out of a much smaller storage system was more than adequate. Now, that doesn't mean we should go and buy, we should sell off half of our external storage or something like that, right? Really what that says to me as a researcher is that this approach is giving us a little bit of headway or headroom in this sort of ongoing little battle between our computational capabilities and our ability to absorb the I/O, right? Our I/O systems have been getting sort of increasingly slow relative to our computational capability. So this is just one more tool that's going to allow us to create reasonable external I/O systems to support computational science. So there's a lot of other things you can do with burst buffers, obviously, or with in-system storage. You can checkpoint just into that. There's no reason why you necessarily have to push every checkpoint off the system, and there's been plenty of research in that space already. You can use some of that space for out-of-core computation, right? These applications that Rob was discussing that were doing a lot of redundant reads might very well have been out-of-core compute operations. The cost of that read is much, much less if we're not going all the way out to the external storage system. You can use that as a holding area for analysis data. So if you need to do some temporal analysis, and you need some amount of data in order to perform that temporal analysis, but you don't really want to write it all the way out to storage. You might be able to capture some of that data in this space, and a number of other different options. There's also some different technologies in terms of types of non-volatile memory that might come into play that could change the picture in terms of affordability and such. And there's also a lot of debate on where this memory might sit in the system. And you can imagine that placing that non-volatile memory near the exterior of the system makes it somewhat easier to use it in this role where it's shifting data between external storage and the periphery of the system. Whereas if you were to integrate that non-volatile memory into each node, for example, that might make it a much better system for certain large data problems, out-of-core problems, things like that. But coordinating movement of data back off to the external system might be somewhat more difficult. And so there's sort of a trade-off and a lot of discussion going on of what architectures make sense in that space. So just to wrap up, relatively complex hardware-software systems that we're talking about. It's useful to think about it from these two perspectives of logically, from a data model perspective, how you'd like to think about interacting with the system, and then having a notional model of the system, how the system behaves, and relative costs of operations that can help you reason about why you might get good or bad performance and where that problem might be coming into play. There are a number of tools. I know you've heard about some other productivity tools this week as well, but there are a number of tools both from software development perspective and helping you manage data and also helping you understand what's happening in your applications that can help. I hope we've given you at least some initial insights into that. You have some ideas on questions to ask. Thanks for listening to us.